All right, works better if I turn on my microphone. Welcome back. We're going to do another example here of how to do a factorial ANOVA. In this case, the example I have is we're returning to the goal setting example. So remember from before, we said that difficult specific goals result in higher performance than do your best or no goals, common finding in the IO literature. So we're going to do that study here. But here I said, but maybe that depends on whether or not you give your employees training. So we have a 2x3 between subjects factorial design here, where half of the participants didn't receive training, whereas the others did. And then we also have another factor where participants were randomly assigned either to get no goals, do your best goals, or difficult specific goals. And we have 36 total participants divided across these six cells. Like always, we start with the source table to get organized, and it's easiest to start with degrees of freedom. So in this case, I had goals had 3 levels, so that's K minus 1, 2 degrees of freedom. Training had 2 levels, so that's K minus 1, 1 degree of freedom. Our interaction term is the product of those 2 degrees of freedom, so 2 times 1 is 2. Remember that we had 36 people total, so we had N minus 1 total degrees of freedom. And our error degrees of freedom is just the difference between our total degrees of freedom and the main effects and interaction terms degrees of freedom. So in this case, 30. So for your homework, I ask you to generate some data. And so that's what we're going to do here. I wanted to generate some data, and I wanted it to have 2 main effects in an interaction. So similar to your homework assignment, I sat down and I plotted what I expected to find. And so here I plotted 2 main effects in an interaction. We can see a main effect of training because on average, if I collapse across goals, there's a difference between the training and the no training condition. Likewise, if I collapse across training and just look at the average of each line, we can see that the lines seem different from each other, that we get higher as we go from no goals to do your best goals to difficult specific goals. And then also the effects of training seems to depend on whether or not we have goals or what type of goals was set, such that we get a strong effect here for the difficult specific goals, but looks like no effect or a weak effect here for no goals. So this is an example of 2 main effects and an interaction. So first things first, plot the data. That's the easiest way. You plot it to get it how you want it to look. So what I did is I just kind of started playing around with means in Excel and plotting this figure until I got it to look how I want. And I landed on these means for my 6 cells. But recall that I have 6 people in each cell. I had N equals 36 total people in my experiment. So in 6 cells, so I had 6 people per cell. And I want there to be variability around each of these means. I don't want everyone just to get the same score within a cell. Instead, there would be variability. So to do that, I used Excel to generate data that will have variability around those means. This looks perhaps intimidating or confusing, but it's actually pretty simple. All this is saying is give me a random, draw a random number from a normal distribution. So you can think about this as there's a population out there somewhere that's normally distributed, and I'm saying give me one value from that. Give me one random observation from that random distribution. I can also say what I want the mean to be of that distribution and how much variance I want around that mean. So for everyone in this cell, they all have the same mean because they're all coming from the same distribution, but their scores will bounce around that mean. Likewise, I do the same thing for the other cells, except here I have a mean of 40, a mean of 60, corresponding to a mean of 40, and a mean of 60. Likewise, 20, 80, 150. Notice that I always have the same variance because I'm assuming that all of these distributions have the same variance, homogeneity of variance. if this, well, let's move forward. Well, I fill in those cells and I get data, right? The Excel program pulled out 6 random numbers from those distributions for each cell and gave me my data. If that using that syntax is confusing or is just not working for you, that's okay. For your homework, you can just generate these by hand. You can just kind of play around with different numbers and make sure that there's variability and that you get the pattern that you want, if that's easier for you. I find this way to be a little bit easier, but it's up to you. If you do go this way, what you'll definitely want to do is copy everything here and then paste values. So you go up into the paste command in Excel and select paste values. And what that does is it gets rid of those equations. If you don't do that, then every time you refresh your screen, these values will update and your answer will keep changing. And you don't want that. So you want to, once you generate the data, go ahead and paste the values. So here's where I started. I was trying to generate this figure and I ended up with this figure. So it's similar, but it's got some variability in it, right? Because it's got some randomness in it that I generated. I'm also going to use Excel to do the math, to do the heavy lifting is what I call it. So first things first, I have my data over here and I need to compute each mean. Instead of writing this all out and getting out my handheld calculator and doing it by hand, it's very tedious and I might make a mistake. Instead, I can use Excel to do that for me. So I can use the average command. So if I say equals average, open parentheses, and then select the cells that I want to take the average of. In this case, I want the no training, no goals average. So I've selected cells B3 through B8. Close parentheses, return, and it will enter the mean there. Then what's handy too is if I need to change these values for some reason, this will automatically update. That might happen if you, because I've asked you to generate data that produce 2 main effects in interaction. Well, maybe you solve everything and you find that one of your main effects is not significant or your interaction is not significant, and you need to fudge the data to make them a little bit more extreme. Well, you wouldn't want to redo all your work, so this way it allows you to just change them and then it will update automatically and then you haven't lost any time. So I do the same thing for the do your best no training condition, which is cells C3 through C8, which I can see down here, so forth for each of the other cells. I can also compute my training condition means, my marginal means, by taking the average of B3 through D8, so everything in the no training, and then likewise through B9 through D14, all the values in the training condition. I do the same thing for the goal means. And finally, my grand mean is just the average of all of the data. Next, I need to compute my sums of squares total, right? I need to subtract each of these values, each of the data points, from the grand mean, square it, and add it up. This can get really tedious if you have to do it by hand. So instead, you can just type the equation one time into Excel and then fill it. So if you hover over this little crosshairs here and drag down, it'll drag this equation down. And you can do the same thing and drag it over. In about 2 seconds, you compute all of these squared deviations. So notice what I'm doing. First, I'm taking the cell B3, so my first cell, and I'm subtracting out cell J5, my grand mean, and I square it. Then I take the next one, B4, subtract out my grand mean, which lives in J5, square it, and so forth. Notice something else. There's no dollar signs around the B3. That's because I want this to fill when I pull it down. When I drag this down, I want it to pull down to the next one. So I typed in B3, but if I pull it down to the next cell, it'll automatically fill in B4. Very handy. But I don't want that to happen here. I want it to always grab cell J5. I don't want it to fill down. So I put dollar signs around that. That's all there is to that. Then I want the sum of squares. So I simply take the sum of all those square deviations that I've just computed, and I've popped them down here. I can come over to my source table and now fill that in. So whereas computing that sum of squares would have been very, very tedious if I did it by hand, in Excel I can do it in about 30 seconds, if even that. It's very fast, and Excel doesn't make mistakes. So whereas you might make a simple mistake just because you typed in your calculator wrong or maybe wrote something down on the paper wrong, Excel doesn't make those mistakes. This is good. I don't want you spending your time and energy crunching numbers, right? That doesn't help you learn statistics. Instead, let's let the computer do the heavy lifting, and we can spend our time thinking about the higher level things that we're trying to do here. So next, we want to compute our sums of squares for our goal condition, right? Just as we did before. So here, I'm taking the mean of my no goal condition, which lives in G5, subtracting out my grand mean, squaring it, and multiplying it by the number of people who are in the no goal condition. Shown here, there's 12 people. I can do the same thing for the do your best goal condition and the same thing for the difficult specific goal condition. Then I simply take the sum of them, and that is my sums of squares for the goal condition. I come and pop it into my source table. Let's do the same thing for the training condition. My mean for the no training group lives in J3. I'm subtracting out J5, my grand mean, squaring it, multiplying it by the number of people who are in the no training condition. And this time it's 6, 6, 6, 18. I can do the same thing for the training group and take the sum, pop that into my omnibus table. You probably see where I'm going. I do the next thing to compute sums of squares cells. Remember, I have to compute sums of squares cells before I can compute the interaction term. So I simply do it for each of my means. Here I'm showing subtracting out the no goals, no training mean, which is in G3. Subtract the grand mean, square it, multiply by the number of people in that cell, 6. I do that for each of my 6 cells, take the sum, and that gives me sums of squares cells. Remember, sums of squares cells is not my interaction term. Instead, I have to take my sums of squares cells, which lives in G19, and subtract out my sums of squares from the training main effect and the sums of squares from the goals main effect to get the interaction sums of squares. I can pop that in right there. Finally, my error term is just what's left over. I can subtract out, subtract the goals, training, and interaction sums of squares from the total sums of squares to get the error. My mean squares, I just divide across. And my F, I divide each mean square by the mean squared error. In this case, I looked these up in the table and I found that I have a significant main effect of goals, a significant main effect of training, and a significant interaction. So given that my goal was to generate data that had significant main effects and an interaction, I've accomplished it. If I had found that one of these terms wasn't significant, I could go back to my data and adjust them to try to make that interaction more extreme. So maybe it looked like this, and I could make it maybe look more extreme than it was. And then all my values would update because I did it in Excel, and I wouldn't have to worry about redoing everything by hand. Again, it's not my goal to have you writing a ton and doing a bunch of work by hand. My goal is to have you do it by hand so that you learn it. But really that means when I say do it by hand, I mean thinking, not just letting SPSS do the numbers, but letting you think about it and crunch the numbers but let the computer do the actual heavy lifting here so we don't make arithmetic errors. So let's consider our simple effects. What are the simple effects of training on performance in the 3 goal conditions? So here, we're looking at the effect of training at no goal. We want to see the effect of, I'm going to go back and look at the plot real quick. We want to see the effect of training from training to no training, but only at the no goal condition, because this is a simple effect. Remember, we just computed main effects. Does training on average have an effect? But what we care about now is at the no goal condition, just the triangle line, does training have an effect? So we're only looking at the no goals condition and the marginal mean here. So we can subtract the mean for the no training cell from the marginal mean, 24.2, square it, and multiply by the number of people in that cell. There are 6 people in that no training, no goals cell. We do the same thing for the training, no goals cell. Subtract out the mean from the marginal mean, square it, and multiply it by 6. And we find the sum of the squares for training at no goal is 172.86. We can do the same thing for the do your best goal, and we can do the same thing for the difficult specific goal. Remember, we pop them into a simple effects table, and for the error term, we use our omnibus, mean squared error and degrees of freedom. So this was from the omnibus test that we computed initially. Each one has 1 degree of freedom because there were only 2 levels of goals, 2 minus 1. Yet our degrees of freedom for our error term belongs to this mean squared error. It's from the omnibus test. So we have F's with 1 and 30 degrees of freedom, 1 and 30. So our F critical is 4.17. Thus, there was no effect of training at the no goal condition. That line, even though it trended down slightly, was non-significant. That downward trend was just error, just sampling error. But the training at do your best condition was significant, which I've indicated with an asterisk. And same thing for the training at the difficult specific goal condition, because these values are greater than our F critical value. Let's go the other direction where we have 3 levels now. So what are the simple effects of goals on performance at each of the 2 training conditions? So here, if I'm looking at the no training condition, I have 3 levels of goals. I compute the sums of squares in the same way. The cell mean minus the marginal mean squared times the number of people in the cell, and I do that for all 3 cells. And I can do that for the no training condition and the training condition. Pop them into my source table and see that I have significant effects. But think back to the one-way ANOVA. When I had 3 groups and I had this significant F effect, I didn't know which group was higher than the other. And that's the boat I'm in now. So when I was doing the other simple effects, when I was just comparing training versus no training, and I saw that I had a significant effect, I could just go look at the means and see which one was bigger. And I knew that that one was higher than the other one because there were only 2 to compare. But now I have 3 means, right? I have training at no goals, the effect of goals at no training, and now I'm comparing no goals to do your best goals to difficult specific goals. So this omnibus tells me that within the no training condition, at least 2 of those means are different, but I don't know which ones. I'm in the same boat as I was before with the one-way ANOVA. Right? Looking at the effects of training at no goal, this is non-significant, so those 2 means are the same. This one is significant, but there's only 2. So I can see that the training mean is higher than the no training mean. Likewise, I can see that the training mean here is higher than the no training mean because I have only 2 levels. But going the other way, goals at no training, there is an effective goals. These 3 means, at least 2 of them are different from each other, but I don't know which ones at this point. Likewise here. So I need to do some more follow-ups. And for this case, I can use t-tests. So I want to compare these 3 means to each other. And to do so, I can use the mean squared error as my estimate of error variance. I know I have 6 people per cell, and so I can go ahead and find the least significant difference between them. But recall that I'm making actually 6 comparisons now because I'm doing it in the training condition and the no training condition. So whereas if I only had 3 means, I could use the t-test with no problem. Here I'm actually making 6 comparisons. And thus, I might want to apply a Bonferroni correction here just to be safe. For each per comparison, I might want to use a more stringent alpha to keep my experiment-wise alpha consistent. So in this case, since I'm making 6 comparisons, and I want to keep my experiment-wise alpha at 0.05, I probably want to use a per comparison alpha of 0.008. Since I don't have that in the table, I think rounding to 0.01 is good enough. So instead of using a t-critical of 2.042 that I would with a 0.05 two-tail test, I'm instead going to use a critical value of 2.75 in order to account for the fact that I'm actually doing 6 tests and I don't want to commit a type 1 error. So I'm using a Bonferroni correction here. So my t-critical is 2.75, and I can cross multiply and solve and find that my least significant difference is 14.82. So the difference between the no goals mean and the do your best goals mean is 13. So that's non-significant. The difference between the difficult specific goals and the no goals is 28. That's greater than 14.84. So that is significant. And the difference between the do your best and the difficult specific goals is 14.84, which is bigger than 14.82, so that is also significant. I can go ahead and do the same thing within the training condition. Here, they were all different from each other, which makes sense. Remember how my interaction was more fanned out under the training condition than under the no training condition. Whether or not we need to do that Bonferroni correction is sort of a judgment call. I was just showing it to you as an example of something that you might want to do, or a reviewer, like a thesis advisor or an external reader might push you to say, well, you're making a lot of tests, you might want to do that. I don't know that there's really you always do it under this condition. It's sort of more of a judgment call. A lot of statistics is about forming an argument. No one knows what the truth is, right? We are making guesses about the population. We're making inferences. And so it's our job to try to balance being conservative and limiting type 1 errors with being too conservative and then making type 2 errors. So in that case, I used a Bonferroni correction. You might do that, you might not. Students always ask, well, what do I do on the test? It'll be clear. I will be clear about what I'm asking you to do. So you don't have to worry about it so much in that regard. All right, well, I will see you next time for repeated measures ANOVA.